Greetings, Earthlings of Analysis and Approaches HL. We're finishing off chapter 16. When we left off in the previous video, we were discussing the derivative function, which perhaps could be better named just the slope function or the gradient function. It literally tells us what the gradient of the tangent line to a curve would be at any particular point. When the original graph is increasing, we're going to see a positive gradient. When the original graph is decreasing, we're going to see a negative gradient. When it's horizontal, we're going to have a gradient of 0. And those are all going to correspond to y values on our derivative function. So we kind of visualized that, thought about what it meant. Now we're going to talk about how to actually calculate that, just by extending the idea from section C. There we calculated the gradient of the tangent line to a curve at a particular point, a comma f of a, by using this limit definition. And so now we're just going to generalize that to any point x comma f of x. A point of vocabulary before we move on: if we can calculate the derivative of a function at a particular point, then we're going to say that that function is differentiable at that point. In most cases, we're going to have functions that are differentiable on large intervals. So perhaps a function will be differentiable on all real numbers. In that case, we'll just say the function is differentiable, end of sentence. Otherwise, we'll state that the function is differentiable on a particular interval. More on that later. Okay, so what we're looking at here is exactly what we saw back in section C. We're just replacing all of the a's with x's. So there's nothing particularly new here. What we do have down at the bottom of the blue box is the definition of the derivative. And this appears in your formula book on page 12. It is called the derivative of f of x from first principles. And occasionally the IB does ask you to calculate derivatives of functions using first principles, and they will explicitly state that they want this particular method used, so you need to use this method and not any shortcuts that we're going to learn in next chapter. So let's look at some of those. Okay, so we're using first principles here to find the gradient function f prime of x of this function here, f of x equals x to the fourth. So we're going to use our definition from the previous screen. In this case, f of x is x to the fourth, so x plus h, or f of x plus h is going to be x plus h to the fourth. And then we're going to have to expand all this, because if we don't, we're just going to get 0 over 0. So we do a binomial expansion, we cancel out anything we can, and then we can factor out the h's, and then cancel one from the denominator. And now we reevaluate, and when we substitute h equals 0 into this, we simply get 4 times x cubed. Then we can do part B, f prime of negative 1. That's easy. That's just 4 times negative 1 cubed. As for the interpretation of that, that's the slope of the tangent line to the curve y equals x to the fourth at the point negative 1, and I guess his y value would be 1. Here's another one. F of x equals 1 over x. So we use our limit definition. Limit as h approaches 0. 1 over x plus h minus 1 over x, all divided by h. I substitute in 0 into that for the h's. I get 0 over 0. No good. So we do some algebra. I'm going to combine those two fractions in the numerator, yeah? So we're there. But that h in the denominator is really h over 1. And so now we can simplify some things, because those are going to cancel. And now when I multiply by the reciprocal of that, then that h is going to cancel with that h. This h here is going to just become a 0, leaving me with this. Also works when there are multiple terms in the function. It's annoying, but it works. So we use our limit definition. And then we have to expand the binomial x plus h cubed and do all that other fun algebra. I mean, right away I do see that like the 7 and the 7 will cancel, so that's good. there's our expansion. I spot a few other things. The 2x and the minus 2x are going to go. Also, this 5x cubed, and when we distribute that 5 with that x cubed, they're going to go, leaving us with just this. And this is good. I mean, when you do these, you want to eventually be able to get rid of the h in the denominator. So it's good to see that the only terms in the numerator, or that all the terms in the numerator have h's in them. If there was some extra term that did not have an h, then I don't know, I wouldn't be able to, I'd be dividing by 0 and I'd have a problem. So this is a good thing to look out for. Another thing to look out for is please don't forget to recopy your limit expression at every line. If you just say that this is equal to that fraction, well, that's not true. It's equal to the limit of that fraction. Anyway, here now we can cancel out the h's, and we're left with our answer, 15x squared plus 2. Now, again, if you know calculus already, then it's frustrating to have to go through all these steps, because to calculate f prime of that, you do it in your head in like less than 2 seconds. It's so easy. So when we get up to the derivative rules next chapter, you'll see how much faster and easier these problems can get, although the questions get harder then, so it kind of balances out. But yeah, unfortunately, like I said, the IB does ask for first principles differentiation sometimes, so we need to be able to do it. Now, in the formula, in the course guide, excuse me, they explicitly state that we only need to use first principles differentiation for polynomial functions. The next example I'm going to show you, however, is not polynomial, but there's some good algebra and trig going on in this one, so it's a good example to look at. Now, this limit here, you maybe recognize it. I mentioned it back in the limits video as an additional special trigonometric limit that a lot of other calculus textbooks will include as something to be memorized. The IB does not require this one. But here it is. We're going to prove that this limit is equal to 0. So let's do some algebra because, again, when we substitute in h equals 0, here we're going to get 0 divided by 0. So we're going to start off by just kind of being clever. We're multiplying by the conjugate of our numerator in both the numerator and the denominator. This is just a trick that works to handle a lot of complicated limits. From there, we use some trig substitutions. So we have cosine squared minus 1. That's the same as negative sine squared, right? Because sine squared plus cosine squared is equal to positive 1. Then we can break this limit up because we have a product here, right? We have, if we just interpret this as sine over h, so we just take one of those sines and that h multiplied by the other one of those sines, we'll make it a negative 1 over that piece, then we get the product of two limits down below. We know this limit here on the left is equal to 1, right? That's our trig limit that the IB does require us to memorize. So really we're just dealing with 1 multiplied by this limit, but this one here, as h goes to 0, this is just 0 divided by 2, which is 0. So we have 1 times 0, which is 0. And we're done. And now we're going to use this, hence, to find the derivative of sine of x, which again is something that eventually we'll see the derivative of sine so often you'll have it memorized, even though it's in the formula book. So like, I know the derivative of sine is cosine, but let's prove it now using this. We're going to use first principles differentiation. Now we've got sine of x plus h. Ooh, that's the compound angle formula. So we break that out. And now we can do some factoring again. Take a moment. Let's see what's happening here. We've got the sine times the cosine, and then the minus sign there coming down here. And then that's headed there, and then everything's divided still by h. And then we see on this end, we've got the limit of, or we've got sine of x times the limit of this piece here, but we already established that that's equal to 0. So this entire term here on the left is going to be 0. And on the right, we have cosine of x times this limit here, which we've established is 1. So it's just cosine times 1, which is cosine. Take a real close look in there. Remember that some of those are x's, some of those are h's. We only care in our limit about what h is doing. So that's why we're allowed to factor out the sine of x and the cosine of x. And we're not treating them as parts of the limit because the limit doesn't care about x, it only cares about h. So that was just one example of a non-polynomial differentiation by first principles. You can see it's definitely a little bit more challenging because we had to establish some special limit in order to get to our conclusion. So establishing derivatives of things like the exponential function, logarithmic functions, etc. This is all going to be way tougher than dealing with polynomials, so that's why we're only required to know how to do those in this course. Last thing I want to talk about in this section is just some alternative notations. So there's a lot going on this screen. We don't really need to worry about all of it. So right now we're using f prime of x to represent the derivative function. That's if our original function was f of x. If our original function was y, then we can write the derivative as this thing here, which we just say dy by dx. This becomes pretty important once we get into applications of derivatives. So we're just going to get used to seeing it for right now, but I want you to notice that it's the derivative of y, that's in our numerator, with respect to x, which is in our denominator. It tells us which is the independent variable and which is the dependent variable. It's not a fraction. I know it looks like a fraction. We've got that fraction bar happening there. It's not a fraction. Even though we're going to kind of treat it like a fraction at times, it's not a fraction, but we'll pretend that it is. I don't know. And you can kind of see that it kind of looks like the slope, right? Like it's kind of like the change in y divided by the change in x. And it's essentially what it is. It's the change in really, really small y divided by the change in really, really small x. And that's what's happening here with these, that we've introduced delta here, delta y and delta x. But whatever. What you really need to know is that dy dx means the exact same thing as f prime of x. They're just two different notations that were developed by two different human beings who lived at different times in different places. Dy dx, as it says here, was developed by Gottfried Leibniz. The f prime of x notation was developed by Joseph Lagrange. We have other notations developed by Euler and Newton. And it's just in different contexts of mathematics, different derivative notations tend to be used. Sometimes one is more preferable than another. Sometimes it's just like historically in this like subsection of mathematics, we use this notation. Sometimes it's just like, oh, you know, for this particular problem, the work is neater if you use one notation over the other. And so, you know, we'll see when we solve differential equations, for example, I like dy dx notation because it allows us to use a technique called separation of variables that you really can't do with f prime of x notation. So there's times when one notation actually is better than the other, but for the most part, for what we're doing, it doesn't matter. I'm pretty sure that if a problem told you to find an expression for f prime of x, and your final answer said dy dx equals whatever it is, that you would get full credit for it. I don't see any reason why you shouldn't. And last thing for this section, we've been dealing with this limit definition of the derivative, but we could also think more directly in terms of secant lines. If we have a particular value x f of x, and then we consider a point really close to it, c f of c, the limit as x approaches c would also give us the slope of the tangent line. And there are times when using this definition can be a little more algebraically preferable to establish what a derivative is or that it doesn't exist. But I would say the vast majority of the time in this course, we should be using the one that's in the formula book. And finally, we spoke about differentiability earlier. This is a really important concept. If a function is differentiable at a particular point, then it must also be continuous at that particular point. Using the contrapositive, so kind of reversing everything here. If a function is not continuous at a particular point, then it is not differentiable at that particular point. However, the converse is not true. A function being continuous does not mean that it must be differentiable. That's a whole lot of words that might not all make sense just yet. Let's see if we can say it a little bit differently. Remember that continuous means that we can draw the function without picking up our pen. Differentiability can be described as just saying that the function is smooth. So if a function is smooth, then we must be able to draw it without picking up our pen. However, just because we can draw a function without picking up our pen does not mean that the function must be smooth. What do I mean by smooth? Well, I mean, smooth. It's going to be all curvy and stuff. It's not going to have a corner, and it's not going to have what we call a cusp, which is kind of like a curvy corner. A good example of a corner would be the absolute value of x. A good example of a cusp would be x to the power of 2/3. In both of these examples, if you zoom in at the origin, you're always going to see that corner or that cusp. It's never going to get smooth. It's never going to get, to use a phrase from a previous video, locally linear. You're always going to have that corner or cusp, and you can't have a tangent line at a corner or a cusp, right? There's no, like, where does the tangent line go at that corner? Does it go that way? Does it go that way? Does it go that way? We don't know, so it's not differentiable there, okay? Now I'm going to show you some algebra that the book uses, and this is nice for certain problems to test whether a function is differentiable, although I usually don't think about it in these terms. But it's kind of similar to how we defined continuity. For a function to be continuous, we said that the limit, the left-handed limit and the right-handed limit needed to exist and needed to be equal. So here we're going to say the left-handed derivative is the derivative as we approach from the left, and that needs to exist and be equal to the right-handed derivative as we approach from the right. So let's look at a couple of examples. The first one's out of the textbook, so we'll see this notation being used, and then I'll kind of do some other stuff my way, and hopefully we'll get a good sense of what's going on. So here's the absolute value of x, and we're going to prove that it's continuous but not differentiable at x equals 0. So continuity, we're going to show that the limit as we approach from the left is the same as the limit as we approach from the right. As we approach from the left, absolute value of x becomes negative x from the algebraic definition of it, and negative 0 is just 0, and from the right, positive 0 is just 0. Those are the same, so it's definitely continuous at x equals 0, and we know we could draw that without picking up our pen. As for it being differentiable, we consider the derivatives from the left and the right. And you can kind of just look at this geometrically. I mean, from the left, that derivative is clearly negative 1. That derivative is clearly positive 1. Those aren't the same, right? Since they're not the same, it's not differentiable. Another way to consider this is that the graph of the derivative of this function would be drawn out in two pieces. And since those don't connect, the function's not differentiable. We can also just use first principles like normal here. And then since we're showing that it's not differentiable at 0, we just put in x equals 0. And then we get here again. And so the numerator's got to be positive, but the denominator is going to be positive when we approach 0 from the right. It's going to be negative when we approach 0 from the left. So again, those two aren't equal to each other. Therefore, this limit doesn't actually exist when x is equal to 0. And that's how I'm used to thinking about it. I'm not at all used to using this left and right-handed derivative notation. but it gets us to the same place. For x to the 2/3, without writing everything out, we could calculate its derivative using first principles, steps not shown on this screen. But the answer we'd get is 2 over 3 times x to the 1/3. Now I know that this is not differentiable at x equals 0 because f prime of 0 is undefined. We could think of it in terms of left and right-hand derivatives by saying, well, as we approach 0 from the left, our derivative is essentially going to negative infinity. And as we approach it from the right, it's going to positive infinity. And since those, well, A, those limits don't exist, and B, they're not equal to each other, so it's clearly not differentiable at 0. But I would just look at this expression and say, like, hey, obviously, when I put in 0 here, it doesn't work. We run into a similar issue here with x to the 1/3, although now the left and the right-handed derivatives are the same because of the fact that we're squaring it. So if x is going to 0 from the right, then we have a positive number squared, still going to be positive, and then we take the cube root of that. Whereas if it approaches 0 from the left, we have a negative number, still squared, which makes it positive. So the limits end up being the same, except still in both cases we're going to infinity, so that limit doesn't actually exist. And if you were to graph this function, it looks kind of like a cubic but turned on its side. And what you end up having here at the origin is actually the tangent line would be completely vertical. And so the slope of that tangent line is undefined. So we say that it's not differentiable at the origin. So that's kind of a weird case. But if you want a really weird looking one, we've got x times sine of 1 over x, of which I've copied a graph of it from Desmos down below. So visually, you can kind of see that there's not going to be a particular tangent line slope at x equals 0 because the function is oscillating faster and faster and faster as we get in here towards 0. So the slopes of the tangent lines are therefore oscillating back and forth between positive and negative values faster and faster and faster as we get closer to the origin. So they're not going to settle down into any particular point as we get in there. If you were to keep zooming in on here, you'll just keep seeing it oscillate. So there's clearly not going to be any derivative there. The derivative function is defined using rules that we will see in the next chapter. So I'm not doing first principles here, but this is still an easy derivative to calculate. And we see just from the algebra there that this also should not exist when x is equal to 0 for, we're dividing by 0 3 times here. So there's obviously a problem. Although I guess it's fair to note that this original function is also not even defined at x equals 0. But I don't know, it was a cool thing to look at, right? One other weird one, I don't really think the IB deals with stuff like this, but say we had this function, and again, we can use first principles ideas to come up with its derivative, but the thing is, this function, its domain is not all real numbers. This function's only defined for x greater than or equal to 0. So it's got an endpoint. The question now is, does its derivative exist at that endpoint? If I look at the formula that I got here, yeah, I can put in 0 into that, and it's equal to 0. But according to the rules that we just saw, for it to be differentiable at a point, the left-hand derivative needs to be equal to the right-hand derivative, which clearly can't happen here because the left-hand derivative doesn't exist. So this function would not be differentiable at 0. And that also kind of makes sense geometrically because we have function looks something like that. Well, what is the tangent line going to be at the endpoint? I can visualize what the tangent lines are going to be as we get closer to the endpoint. But when I get exactly to it, like we could say it's 0 because it's getting closer to 0 as you come from the right, but I don't know, at the endpoint, I feel like I could connect it any way that I wanted to. So something like that. Endpoints, we're going to say it's not differentiable. We'll describe functions as being differentiable on open intervals. This function is certainly differentiable on the function or on the domain 0 to infinity. It's just not differentiable on that 0 to infinity. I'll finish up by doing just one problem out of the homework set from the textbook. And this is a popular enough topic. The IB has definitely asked a couple questions on this on previous exams, but it used to be in the calculus option, so it wasn't represented too heavily. But I think it's going to have a good chance of showing up more often in the paper 1 and 2 for the new course. And AP Calc asks a lot of questions like this as well. So we're going to revisit this question type later on once we know how to take more complicated derivatives. But just to give you a taste of it for right now, we're given a piecewise function, just like, I mean, absolute value is a piecewise function, so similar idea. And we're told what its pieces are, and we're told where those pieces are defined. Wonderful. And we want to figure out what C and D are so that this function is differentiable at x equals 1. And x equals 1 is crucial because that's where those two pieces meet up. Trust me, it's differentiable at every value to the left of 1 because x squared is differentiable. I know that because I know x squared is a smooth curve. It's also going to be differentiable every place to the right of 1 because cx plus d is a line, and a line is going to be differentiable everywhere. But the question now is it differentiable at that boundary point at x equals 1? So let's calculate some derivatives here. Again, I'm using first principles, but I don't have the time to write all this crap out, right? So for the x squared part, if you successfully use first principles differentiation on that, you should get 2x. So it'll be 2x when x is less than or equal to 1. And for the linear part, you should just get c when x is greater than 1. So if it's differentiable, this is the left-handed derivative. This is the right-handed derivative. For it to be differentiable, we require, therefore, that 2x is equal to c. And this is how I'm used to doing problems like this. I've never written out the notation with the left and right-hand derivative and whatnot. I've just done it this way. Now 2x equals c isn't an equation that we can solve, but what did I circle above? We're interested only when x is equal to 1, so that means that c has got to be equal to 2. Unfortunately, that doesn't tell us what d is. So what can we do now? Well, remember that if it's differentiable, that means it's also continuous. And if it's continuous, that means that x squared has to be equal to cx plus d. We already know that c is equal to 2, and it's got to be continuous at the boundary point when x is equal to 1, leaving us with 1 equaling 2 plus d, so d is going to be equal to -1. So the graph of this piecewise function is going to have a parabola up until 1 and then a line from there onward. It's going to be continuous, and it's going to be absolutely a smooth transition. If this slope were any different than 2, then we actually have a corner there, but these two graphs are put together just perfectly. That's a differentiable curve. Okay, so that's the main idea with a problem like this, but like I said, if we're going to actually see these problems, it's really going to be with much more complicated functions rather than just a quadratic and a linear, and we're going to do them after we actually know the derivative rules. We're not going to be doing first principles differentiation with a problem like this, so I just wanted to show it to you since the textbook has it in this section, but really we'll practice this later on. And finally, last thing I promise, I'm so excited that the book included this in this publication because the previous curricula versions of the book, it didn't have this function in it, and I always had to talk about it. But I'm so happy it's here. So there's this thing, and it's called the Weierstrass function. Okay, and you don't need to worry about what this first paragraph is going on about. Um, yeah, whatever. So it's called the Weierstrass function because it's named after this dude, Karl Weierstrass, who figured out what it is. And this is a function that is continuous everywhere, but differentiable nowhere. Exclamation point. Because that's like, what? How is this even possible? Here's a picture of the thing. So you can draw this thing without picking up your pen, but as you zoom in any place, all you get are corners. It's literally all corners, and this is the weirdest thing, probably the weirdest function I've ever seen in my life. Anyway, we're not dealing with any of this nonsense in our course, but that is just so good, right?